Now, we could do the same thing with proportions. So we want to see the difference between proportions. And we might do this in a way that says we have two samples where we have a number of successes and failures. If we're sampling, let's say, parts or that come off an assembly line, or yes-no responses, or approve or disapprove responses. So let's say we were trying to calculate whether or not one sample voters would say yes to a proposition or no to a proposition. We would take two samples and we want to see if the two samples are, what their confidence intervals are. Our formula is similar to what we had before. In both cases, both are from the proportion as well as the difference of the means. We see that we have the proportion 1 prediction point estimate minus the proportion 2 prediction estimate, plus or minus the z multiple, again, as we had discussed before, times the standard error of the difference between the two. The difference between the proportions is calculated by the difference of success in sample 1 minus the difference in success for sample 2. So this is a difference from the x mean, or the sample means, but it's a similar concept. Our standard error for the difference between the proportions is a little bit different. This is going to be equal to the square root of the prediction of success for P1 for sample 1 times 1 minus P1 over N1. So you remember that this part looks like the way it was for a single proportion, a confidence interval for a single proportion. But now what we're going to do is we're going to add for the second sample the same thing. So the predicted success for sample 2, P2 hat, times 1 minus P2 hat over N2. And then we will take the square root. So here's our sample. From the data set on the right, we have 300 tests of products, success and fail. So did the items pass our test or fail our test? We have 2 trials, but we only show 20 here. So 1 means success, 0 means failure. We want to obtain a confidence interval between the difference proportions in the 2 trials. The success in trial 1 was 0.56 and the success in trial 2 was 0.64. Therefore, we have the following formula: P1 hat minus P2 hat plus or minus the z multiple times the standard error of the P1 hat minus P2 hat. Again, we calculate our z multiple using the norm.s.inv 0.975, because again, it's a two-tailed test, so we need to divide this by 2 because we do not have a direct two-tailed test in Excel, and this will give us 1.96. So we have P1 hat minus P2 hat, which equals negative 0.08. So our standard error was now calculated as the square root of 0.56 times 0.44 divided by 300, plus 0.64 times 0.36 divided by 300, and this gives us a value of 0.04. So therefore, our confidence interval will be negative 0.08 plus or minus the 1.96 that was calculated from the z multiple times 0.04. And therefore, we have a lower bound of negative 0.002 and negative 0.158. You'll notice that this does not cross 0, and when the confidence interval does not cross 0 in terms of the difference between the proportions, that is an indication that there is a difference between the 2 proportions. If it crossed 0, as we had said before with the means, it would mean that there was a probability that it was 0, and so they would be statistically equivalent. But in this case, because it doesn't cross 0, then that's not the case. We would say that these 2 samples are very different.